All right, am I there? Can people
We,
see
we
everything?
hear you and we see you, Kevin.
Perfect, thank you so much. And thank you, Thomas and Maxime, for organizing this thing, and for all of you showing up at whatever time it is for you, especially you, Min. It's nice to see so many familiar names in the participants list. And I'm just going to talk about some of the work that we've been doing. It's sort of in this theme, as far as I can understand, of the previous talks, which is to take multidimensional spectroscopy and put increasingly more complex things into the sample position. And so what I'm going to be talking about today is putting in things that either do chemistry or things that we hope will do chemistry, which is either, on the one hand, electrocatalysis and electrochemical cells, and on the other, optical cavities, where we hope that we can control chemical reactions through the coupling to cavity modes. All right. And of course, I want to thank my group, the people who did this work. Actually, it was a pretty good team effort on all the projects here, particularly Rong working on the Polaritons, and Laura working on electrochemistry, and Lindsay as well, with help from everybody, especially Joseph Mastron for getting the 2D set up in Lumos working so well with Rong. So this is all work that was done during the coronavirus pandemic, which is surprising that everyone was able to be safe and work so hard. But I'd love to get rid of this thing, so hopefully that will happen soon enough. Okay, so electrochemistry is a topic that when I was starting in graduate school was not on most people's radar. You looked up the tables in the book, and then you figured out what the reduction potentials were. You calculated some, equilibrium constant, and then you went on. But now we're starting to realize that even after we solve the coronavirus pandemic, we're going to have a bigger challenge ahead of us, which is essentially how to stop climate change. And one way is to try to get rid of carbon dioxide by doing some sort of chemical approach. Photocatalysis is a good way, but then you have to develop your light absorbing step and your chemistry step together. Electrochemistry allows you to rely on mature technology like solar cells, which are only going to get better, and basically put all the challenge onto the electrodes and to the molecular catalysts that are there. And so in the community of electrochemists and electrocatalyst scientists, it's very common to do electrochemistry while doing spectroscopy. So I'm just showing one example on the right from the work that was used to elucidate the mechanism of rhenium bipyridal complexes to do electrocatalytic reduction of carbon dioxide. And this is a really powerful technique, but it's not new. You see that 1992. And so the question we had and other people had is, can you adopt our very powerful spectroscopic methods to address these problems? All right, and so what's interesting, one of the challenges that you have here is that there's a lot of chemical species during an electrochemical reaction. You'd like to be able to sort them out, assign them if possible. That would be very helpful for the inorganic chemists who have been studying this already. Now we're starting out with a system that's pretty well understood, but you can imagine, of course, that we would apply this to systems that aren't so well understood, so that some of the initial discovery could in principle be done with 2D-IR spectroscopy. So the workhorse model system is this rhenium bipyridal tricarbonyl chloride, and there's many derivatives of this. And what you can see is that as you apply voltage, you can see the decrease in the concentration of the starting material, the starting catalyst number one. And as you decrease the voltage and change the driving force for electrochemistry, you can drive motion around this, electrocatalytic cycle. Okay, and there's some species that are pretty much well understood and characterized, and thank goodness for that, because then we know sort of what we're looking at when we do our earlier spectroscopy methods. An example is this dimer species here, which is a rhenium dimer. As you can imagine, that's not particularly useful for carbon dioxide reduction. So this is viewed as something that you'd like to avoid if you can. And so figuring out what you can tweak in your catalyst or your environment to avoid the dimer would be, for example, a benefit. That's one concrete example of how being able to unambiguously assign what you're seeing could help in the design process of better catalysts. Okay, so people on this Zoom meeting have contributed greatly to the introduction of electrochemistry to 2D-IR spectroscopy, particularly Peter's group using the ATR cell. We're also working on building one of these too. It's a great way to do things, particularly if you want to look at the species that's of interest on the surface, which is where, of course, the real electrochemistry, electron transfer reactions take place. We ultimately do have to get to looking at things on the interface, and that's going to be an important way forward in understanding the true molecular mechanisms of the processes. I'm going to be talking about a slightly different view of how to do this, but it's more like the chemical way. But nevertheless, of course, what they did, and I'm sure most of you are familiar with this fantastic work, was to use ATR cell, to use the surface enhancement, and also to use the electrode. And that allowed to do some changing of the voltage, looking at the Stark shift of the carbonyl on the platinum. And then, of course, with 2D-IR spectroscopy, you don't just get frequencies, you get the dynamics. And so you can see the change in the centerline slope at different potentials. In this particular case, since there wasn't any real actual chemistry happening, then most of the dynamics comes from the solvation, which didn't seem to care about the potential very much. But you can imagine all kinds of things happening with double layers and so on that will be very important for physical chemists to revisit. I think that there's a lot of open questions in electrochemistry that have been too colloquialized by the electrochemists, and that physical chemists can get back to this topic, and it will be a good thing to do. Another example was by Jens Bredenbeck, also working in a kind of reflection mode. Here's an example of an iron cyanide complex, which you can oxidize or reduce. In this particular case, they found differences in the vibrational lifetime, actually pretty pronounced differences. And he also looked at flavin mononucleotide, which is an important cofactor in biology. Right? So the people have absolutely applied 2D-IR spectroscopy and combined it with electrochemistry. When we first heard about this, we were actually in Oxford, and I saw some work from Tony Vilcek in working with the group from RAL that changed my whole thinking about everything. They used one of these relatively simple cells, the so-called Otto cell, which actually been used for many years, particularly by Franti Hartl, to study things like the rhenium complex. And what it's nice about it is it's in transmission mode. So you get nothing about the interface, which I understand is important, and I hope that we get there sometime. But you can quickly make connection with the way that typical chemists do this. And they want to see what are the intermediates that are actually happening during electrocatalysis. All right, so it's super convenient in the sense that you just stick it into your sample cell in the way you normally would. One of the big problems, which I'll zoom in here, the way most electrochemists do this is they have these mesh grids. And of course, if you look at that and you think about how you're going to do coherent spectroscopy with mesh grids, it's a problem. So Franti had the brilliant idea of just cutting a hole in the mesh. And so your laser beam can go through the hole or around it. We found that also works. And this design has 3 electrodes, just like you would expect in a 3-electrode electrochemical cell. The working electrode, for example, is where we'll reduce the rhenium complex. All right, so it's conventional in the sense that we can link to traditional electrochemistry. There is some scattering, but it's not that bad, and you can actually, it's the same kind of scattering you would normally have in your experiment with sample windows, and we find that it actually works really well. There's some interesting hiccups that occur though when you do electrochemistry for real, and that I was so naive when we started this. I thought, oh, this is really cool. We can just like pulse the voltage, and we can turn on and off oxidation and reduction. And then you actually read the electrochemistry papers, and they're like, how they tell you how fast they scan the voltage, right? And it's not that fast. So this is actually a non-equilibrium system inherently. And so since it's non-equilibrium inherently, that means you turn the voltage on, you have to wait a certain amount of time for a steady state population to build up. Now you could literally wait for it to reach a steady state, but that's gonna take a very long time. So what we decided to do instead is to realize that all we're really doing is changing the concentration of species as a function of time. So if we have a way of measuring the concentration of the species as we do our 2D-IR experiments, then we can essentially correct the amplitudes of the peaks as a function of time if we want to analyze things like IVR, population transfer, or whatever, spectral diffusion. So that's what we do. We use one of the beams in the experiment. So we basically take the tracer beam that would normally, sort of tell us where our signal is, and we unblock it. We block the other beams in the experiment, the local oscillator and the pump beams and the probe, and then we can measure a tracer absorption, basically a tracer transmission at each, before we do every single 2D-IR spectrum. It's very simple interfacing with our normal software for doing 2D spectroscopy, and then we can just go ahead and do the experiments. If you're using a pulse shaper, it's even easier, just block the pulse-shaped pulse and you just look at your transmitted probe, and you can monitor your transmission, and that allows you to correct for these slowly varying but non-equilibrium population changes. All right, so that's what I mean when I say the normalization. All right, so does 2D spectroscopy work? Well, of course it works, because you put it in, you put a voltage on, something happens. With the rhenium complex, it's amazing. It turns purple, so you can tell that it's actually changing. And this is just showing you again that spectro-electrochemical FTIR spectrum at the top, and then below it is the 2D rephasing spectrum at minus 1.7 volts and a half a picosecond waiting time. All right, so you can definitely measure 2D spectra. It doesn't change anything about how we do 2D spectroscopy, except for this having to record the tracer absorption spectrum before each spectrum. In a minute, I'll show you. Sometimes you can get lucky. It doesn't change that much if you wait long enough, and we can then compare. All right, so one of the things that we had to do when you do electrochemistry is it's different from what we've done before with this rhenium complex, is that you need an electrolyte, right? You need something in there to shuttle charges around. So we have the electrolyte, and it's going to change a little bit the dynamics. So we just need a bit different reference point. So here is the rhenium chloride tricarbonyl bipyridine THF, sort of garden variety spectrum. We look at the high frequency peak because it's the best resolved. We look at the spectral diffusion, decay, the decay of the frequency correlation function due to spectral diffusion. We've studied this a lot. We know about how it depends on solvent and so on. So here it is in THF, which is about 3 picoseconds. When we add 0.1 molar of the electrolyte, and we've actually looked at different electrolytes, and they have differences. So that's something that you get in maybe in dynamics-based spectroscopy that you wouldn't see in any other way. Here we see that it slows down the spectral diffusion, not quite a factor of 2, which isn't too surprising. You've added a bunch of electrolytes, so you've certainly increased the viscosity, 0.1 molar, but also you've changed the electrostatic environment. So none of this is shocking. It's just that you need to be a little bit aware of that. Also, the initial value of the correlation function goes up a little bit, so you can imagine that you have a little bit more inhomogeneous broadening. Again, I don't think that's surprising to anybody. It doesn't affect the vibrational relaxation timescales. All right, so then what we do is we measure 2D-IR spectra at different voltages. Here, this is all work, COVID work. It's work that we've done under, let's say, duress. But have still managed to make a great amount of progress. We're looking at basically 1 voltage here. Okay, so 1 voltage where we know we build up a bunch of these intermediates so that we can see something interesting. So I'm showing you now rephasing and non-rephasing spectra. People probably know that non-rephasing spectra has this advantage that you can kind of get a little bit better resolution because of the peculiar interferences of the peaks. So this is particularly useful in electrochemistry where you have a lot of species sort of overlapping or at least nearby each other. And this shows you the FTIR spectrum below and how it matches to the 2D spectrum. Like it's commonly done in a lot of spectro-electrochemistry experiments, people like to often plot the difference spectra. So here I'm showing the difference. I think Jens had a really good example of this with the flavin. And then this is just showing a difference non-rephasing spectrum. You can compute any differences, any spectra differences you want. A lot of times it's not necessary because if you're really building up macroscopic quantities of the different oxidation reduction states or intermediates, you don't really even need different spectra. Okay, so one of the problems that we had, so in the FDR, at the 2D spectrum I showed at the beginning, those 3 peaks are not actually at exactly the same position as the 3 peaks that we have here. And because this rhenium system is so well understood, if there's a few wave number shift, you actually can tell that that's a different chemical species. I know that sounds amazing, but it's true. And so we know from this data here that I'm showing you, which we did during the COVID time, we have the starting catalyst is the high frequency peak. The middle peak is actually a solvent attached cation. And that only occurs when you have a little bit of oxygen, which is always the problem with electrochemistry. We didn't fully appreciate how big of a problem that is, but A student in the group before who set this all up, Lindsay Machaki, learned the hard way that you need to do these sample preparations in the glove box. Well, the glove box died, sometime between when she did that and when we got back in the lab. And because of COVID, thank you, COVID, we couldn't borrow other people's glove boxes, which in this department is usually not a problem, but we're so restricted on what we can do. We couldn't just go to one of the other 5 or 6 glove boxes and just make a sample there. So that's unfortunate. Therefore, there's a little bit of oxygen, but we're 2D spectroscopists, so we call that lemonade, and we just say, hey, look, you can see multiple species and sort them out by not having cross peaks, so we know they're different, things like that. But we do get to see the key singly reduced species there, which is the lower frequency one. And that's sort of getting to the starting point of where electrocatalysis is actually going to take place for this molecule. Actually, you need the chloride to leave, but once that chloride leaves, then this thing is started and ready to go. Okay. Now, what we can do, of course, is measure dynamics, which is not of interest generally to the catalysis community, but it is to us. And so hopefully, if we're clever, we'll figure out ways of linking dynamics to the actual chemical reactivity. Obviously, we don't know how to do that right now, but we suspect that there must be a link. Here, I'm showing you the 2 different potentials. So the green curve on the bottom is just the molecule I showed, the spectrum or the dynamics I showed before. So it's the rhenium complex with no volts, but with the electrolyte. So there's a sort of slower spectral diffusion. And then when we make a negative potential, reduce it, then we see an increase in the initial value. So that says the inhomogeneous broadening has gone up. The spectra line shapes are not that different. So when you see the change in the correlation function, you can pretty much link it to the ready-made interpretation that's because there's more inhomogeneous broadening, and it doesn't decay to 0, that's for sure. And then the reason why we show 2 curves there, or 2 sets of data, one of those sets of data is recorded where we let the system reach a steady state. So we really just sat at that 1.7 volts for a really long time, and then took our full scan. To do 15 picoseconds in our lab takes about, about half an hour. It's about a minute per 2D spectrum. So as many as you need to do that, a minute for rephasing and unrephasing. And then we can, put that data together. So it's about half an hour of measurement time to get that curve. So one of those is when it's lucky and nothing's changing. And the other one was where it absolutely was changing. The populations were changing as a function of doing the actual 2D experiment. But then because we use that tracer normalization, we can go back through and we can scale the rephasing amplitude and scale the non-rephasing amplitude. And that allows us to use the inhomogeneity index method for obtaining the correlation function, even when the system is, nominally or not so nominally non-equilibrium. That's going to be very important because electrochemistry really is a process, and as it's occurring, unless you can do your entire waiting time scan in a second, which no one can do as far as I know, we're not going to be able to get the information that we want. Single 2D spectra, sure, that's no problem. You just want cross peaks or coupling or whatever. Okay, so then let's look at another thing that you might notice. Everyone focuses on the high frequency peaks, and certainly when you look at the tables of these carbonyl frequencies, you do see a lot of assignments for those high frequency peaks. But what about the murky region at the bottom? Those are the the not symmetric stretches. Could you actually assign those or learn anything about them? But because you have 2D spectroscopy, you have cross peaks. And so you can pull out of that murky blob, you can actually pull out what is the associated lower frequency bands. Because of some technical issues with our upconversion approach that some people might know about, it means that our detection bandwidth is somewhat limited, but our excitation bandwidth is not limited at all. So if we take a slice along the excitation axis at like the different species, and there's 3 of them, then what you can see is that there's 3 peaks or 3 sets of data. They're all shifted because of the way that they're shifted. And then we can go through and find what are the low frequency modes that go with each of the high frequency bands. So we're using the high spectral resolution of the symmetric stretches to basically pull out of this murky region the low frequency modes that go with them. You might think, who cares about that? I mean, if you have enough information from the high frequency band, why not? But if you want to compare to some DFT or some other thing, you might want to know what those low frequency bands are. And there's certainly other peaks in the spectrum that we will see when we have our glove box and everything's working. Okay, so just to show you can do this in other solvents and acetonitrile, which is actually more important from the point of view of the people who do the catalysis every day. here's a nice example. I really like this one. This is where we didn't have any problem with the oxygen. So you can see the starting catalyst. Now we're showing it a different spectrum, different rephasing spectrum. The singly reduced species, the one that can do the thing. And then this dimer, which is a problem. You don't want this dimer, but there it is. And then you can study the dynamics of each of those. You can see cross peaks to the other mode of the dimer, which is super good because that allows us to assign that dimer species unambiguously. Whereas from FTIR, you have to like assume that you know something about what the other peaks are. The dimer has a more closely spaced lower frequency mode than any of the tricarbonyls. Okay. So, yes, of course, we want to actually do carbon dioxide. And so Laura has ordered a carbon dioxide tank, and we're ready to go and try to actually make some CO2 electrocatalysis and do 2D-IR spectroscopy on it. And I think that's going to be really exciting. It's going to add, obviously, more complications to our experiments. But I think it's fair to say that doing 2D-IR spectro-electrochemistry is totally doable. And you can start to team up with your inorganic colleagues and talk to them about how your technique is going to be able to help them understand their mechanisms and make better catalysts. All right, so I'm going to switch gears. Instead of putting in an electrochemical cell into your sample, now you're going to put in a cavity. When I started in grad school, the cool thing to do was to do coherent control, to use lasers to control the outcome of chemical reactions beyond just like photochemistry. I really wanted to do that, and I joined Dwayne Miller's group specifically to do that kind of experiment. And at the time, and still, there's a few paradigms for thinking about how you would use light to control reactions beyond just exciting them. So, of course, shape excitation is one way to try to steer wave packets. Another is sort of timing the arrival of multiple pulses that you can then dump a product where you want it to be. And then if you have a really strong laser and you don't care about having no solvent or something like that, then you can just, forego the molecular Hamiltonian and rely on the light to shape the potential energy surface. And there are certainly pluses and minuses to all of these different approaches. But one thing that's coming online right now is the recognition that you can get sort of the best of both worlds. You can get strong interaction between light and molecule, but without having to have a high field. And that way is by putting the molecules into a cavity. Now, if anyone has ever met a physicist, they will tell you that this is a well-known thing, even though in chemistry, we're just hearing about it sort of recently. And that's fine. But that's the good thing about that is there's a lot of the groundwork that's already done. But there are some interesting quirks that come around in chemistry that the physicists probably haven't spent a whole lot of time on. And one of those is an issue that I'll discuss in our one of our latest forays into doing things with polaritons. So I know Tobias introduced this a bit, so I'm definitely not going to go into it very much. I see Wei here. Hi, Wei. We were deeply and importantly inspired by his work, and so I'll show you how ours relates to it too. But the basic idea is you have a cavity mode, and if you make it resonant with a molecular mode, then you can have lots of molecules in your cavity coupled to that cavity mode. And when you do that, you get two sort of special modes. The ones you might think of relating to like your bonding and anti-bonding or symmetric anti-symmetric stretch that you would think of from like molecular orbital theory or a couple of vibrations. And there's two of those, but there's n-1. If n is the number of molecules that are coupling, n-1 molecule, n-1 modes are not part of the so-called polaritons. And those are sometimes usually called dark states. And they are ones that don't have a frequency that splits like you would see when you have the two modes in the chemistry. So they have at least no significant oscillator strength. And what you see then when you look at the transmission, as I'll show you in a minute, you see two peaks. Now, one thing I want to point out, we can stop right here. If you don't know anything about polaritons, it doesn't matter because we have a lot of people who know about excitons. And this looks like a excitonic Hamiltonian, just where you have only two states, a coupling from all the other sites to the cavity site, right? And so you have a J coupling between the cavity and all the molecules. And so we know how to analyze the sort of statistics of this kind of a Hamiltonian. You just assume that maybe there's some disorder, right? You add disorder to the diagonal. In this case, what you can do is you can add this disorder to the molecular states because we're going to put our molecules in a polar solvent. And we want to see what happens when you have a polar solvent molecular cavity. All right, so when there's no disorder, you can calculate something called the inverse participation ratio, which just tells you how many sites are the eigenvectors delocalized over. And if you had, in the case where there's no disorder, if I look at the delocalization of the dark states, so I'm ignoring the two polariton states now, then because there is no delocalization, they're basically stuck on each individual molecule. So you look at the number of states and their delocalizations, like a histogram of the inverse participation ratio, you see it's at 1. But if I add in disorder into the model, which I can do by just adding a Gaussian distributed random variable to the diagonal and doing this many, many times and then making an average of this histogram, then I see that in fact I get a distribution of disorder, I get a distribution of delocalizations. So maybe there is something that we can, take advantage of to play around with the delocalization of these dark states and see how does that affect the dark state interaction with the polariton states. And that's something that Wei was the first to really get at with their studies on the polaritons. One other thing that comes out automatically is something that's, to me, counterintuitive, but it's, again, one of those things that the physicists have known about forever, is that if you look at the disorder of the eigenvalues now, so here I'm just histogramming the values that you get. So if you look at the polariton states, you can make a histogram of them as you evaluate your Hamiltonian many times with Gaussian disorder, in this case, about 3 wave numbers. And you see that they're extremely narrow, essentially as narrow as you can get, whereas the dark states are very broad and they look Gaussian and they reflect the Gaussian nature of the distribution on the sites, on the molecular sites. Okay, so what you should expect to see in what is in the literature is that there's essentially no inhomogeneous broadening for the polaritons, but there could be tons of inhomogeneous broadening or ordinary inhomogeneous broadening for the dark states. Okay, so here's the sort of pioneering work on 2D spectroscopy from Wei and the collaboration with Jeff Rutsky, who's got us all started on ultrafast vibrational spectroscopy on molecular polaritons, where they looked at tungsten hexacarbonyl. Tungsten hexacarbonyl is a perfect molecule for this. Has a very strong transition, only one of them, but it's triply degenerate, and there's 3 Raman modes or 3 other modes that are not that you don't see. So there's a little bit of something that might be hiding in there, but that doesn't seem to matter too much. They found a bunch of really interesting things, and I hope that Wei will give a talk so he can tell you all about it. One of the really interesting features, though, is that you do actually see a signature of the dark state vibration in the 2D spectra. And the one I'll show you later, you see it on both axes, not just here, but you can also see it on along the detection axis. They plot their spectra the other way. One quirk about tungsten hexacarbonyl that's been known for a long time is that its vibrational anharmonicity makes it such that the 1 to 2 transition is actually sort of clear. It can get through the transmission band of this Fabry-Perot planar cavity. And so that means that you have the ability to see the dark state through the lower, because the 1 to 2 absorption, the excited state absorption of the dark state actually shows up where the lower polariton is. Okay, so first thing that we did was tungsten hexacarbonyl. We've done other molecules, but I want to talk about the stuff on tungsten hexacarbonyl because having one vibration is a lot simpler than when having multiple vibrations, which we've also been working on. So with this tungsten hexacarbonyl in butyl acetate, so it's a polar solvent, you actually get a pretty good broad spectrum. The spectral width is about 16 wave numbers for half max, so it's pretty solid broadening for a metal carbonyl and a polar solvent. And here we're just showing you something that Ron worked really hard on, which is to separate rephasing and non-rephasing using our pulse shaper. So we, in our lab in Lumos, we use pulse shapers from both phase tech and from Fastlight. So that's great to see the interaction there with the sponsors. So we can separate rephasing and non-rephasing, and then we can make absorptive. And then the reason we want to do this is because sometimes these spectra are a bit distorted in the polariton. So we wanted to go back to our simpler way of doing the frequency fluctuation correlation function by using the inhomogeneity index, which you have to do extra work when using a pulse shaper because you don't measure the 2 pathways separately. So we separate them out using the method that Jennifer Ogilvy's group discovered or introduced. And it works great. And we have a whole paper that we compare them. And the nice thing about with pulse shapers is you can actually take the same data set and process them the exact same measured things, but we can get the inhomogeneity index or the centerline slope, and we see when they're the same and when they're not the same. Okay, so that's going to be useful because then I can go look at a narrow region of the spectrum and still get the inhomogeneity index, whereas for the centerline slope, you need to look over a large region to get a slope. All right, so in tungsten hexacarbonyl and butyl acetate, you get a 2.5 picosecond spectral diffusion timescale. There's nothing particularly surprising about that. That's fine. But now we take the complex and put it into the butyl acetate in the cavity. And so you see a nice splitting between the band into the lower and upper polariton bands. And the line width is actually narrower than the line width of the molecule in solution. And that reflects this effect that we showed before of the polaritons essentially being immune to spectral inhomogeneity. Right? Here is a sequence of 2D spectra. These are now absorptive spectra. The earliest time happens to be on the right. So this is 1 picoseconds, 2 picoseconds, 3 picoseconds. A lot of the features are exactly the same as you saw in Wei's original data with the tungsten hexacarbonyl in hexane and then in other solvents that they've done. One interesting thing to note here is that you do see the dark state on both the excitation and detection axes. So we plot it the other way. So excitation in this way, detection that way. But you don't see a diagonal peak on any of these. And you can slice it however you want, and you never see a diagonal peak there. We're still trying to sort of understand for ourselves what's going on with that spectroscopic aspect. Again, we separate the rephasing and non-rephasing. And then what we're going to do is we're going to measure the spectral diffusion or the decay of the inhomogeneity index in these small spectral regions using the technique that we've been using for a long time. Okay, so let's look first at the upper polariton. So the upper polariton just is the higher frequency one here. Okay, and it's the one where you don't see any influence of the dark states. So when we look at the upper polariton, we can separate that into non-rephasing and rephasing. These are showing you like the pretty amazing quality data that we can get from the Lumos 2D-IR setup. And so when we take the difference and divide by the sum, which is the inhomogeneity index, then we can show that there's essentially 0 spectral diffusion. This slight offset might or might not be real. That we don't know yet, but there's no time dependence whatsoever. So this is looking like a textbook polariton, which is to say there's no inhomogeneous broadening and then no dynamical signature of that either, meaning there's no spectral diffusion, right? So that's this cartoon here. Now, what about the lower polariton? The lower polariton is the one where, thanks to Wei's, creative thinking, that they realize that you see a dark state kind of getting through some energy transfer process or some direct excitation of the dark state. I actually don't know how we're going to think about it, but somehow you create these excited state dark state molecules, and then you're looking at the 1 to 2 transition. And we looked at the 1 to 2 ESA spectral diffusion time scales. That was how I showed earlier on. A lot of times, of course, people look at the ground state centerline slope or whatever. In many simple systems, the excited state absorption shows you the same dynamics because the 2 states are highly correlated with each other. And so here what we see is extremely obvious spectral diffusion, right? So extremely clear, very, very clean data there, with exactly the same time scale as the dark state spectral diffusion. And so what we're seeing is not, unexpected polariton spectral diffusion. What we're seeing instead is exactly a manifestation of this idea that you can witness the dark states through the lower polariton peak because of the sort of quirky nature of the excited state absorption, but that you see essentially the same time scale for the dynamics. So the dynamics of the dark state is not different from the regular molecules in solution. Okay. So that's what I wanted to talk about. I don't know how I am for time because I wasn't looking at my watch, but I want to thank everybody so much in the lab for working so hard on this during this crazy time. We managed to get safe and productive shifts going. One thing I want to say, of course, is also that there are other things to think about in the future. We had been planning to invite all of you to. We've been planning to host everybody here for time-resolved vibrational spectroscopy in 2021. And that's obviously not going to happen here. So we're going to do something, probably a Zoom symposium. And I hope that just to get this on your calendars. So one thing I wanted to do especially was to give a special shout out to Dr. Yin Song, who has been instrumental in building the Lumos lab. This is a pretty remarkable facility. We love it, and we hope that people will use it in Michigan, but we also want to encourage other people to try to make these facilities available to other communities, because as we're seeing in these talks, that our methods are actually quite general and very practical for answering questions in other fields, but they're very hard. I think everybody understands how hard they are. So we need to be able to broaden our reach, and one of the ways of doing that is to make user-based facilities. And without Yin's work, I don't really think that there would be any dream of us having made this a user facility working as well as it has been doing. So I just want to make sure that first I give credit to Yin, but also I want to encourage all of you to work on. I know a few people have worked on MRI proposals in the US to get sort of center style things. And it's going to be quite a great resource for other users to build your own centers. All right, thanks so much.
Thank you very much. We already have a question. Wei, are you there?
Hi. Hi, Thomas.
Hey, please ask your question.
Kevin. Yeah, hi, beautiful
Hey.
work. So I just wonder, when you analyze for the Polariton work, when you analyze the spectral diffusion, did you analyze the cross peak, and how would the cross peak looks like?
Sorry, you're asking about did we analyze the cross peak?
Yeah.
In terms of what? In terms of the
In
inhomogeneity
terms of the
index of the
FFCF.
cross? No, we did not look at the. Why do you think we should do that?
So I guess it's not surprising for the lower, as you show, for the upper Polariton is purely homogeneous, and then the upper Polariton is inhomogeneous because of the dominating contribution from the overtone state of the dark mode. But I'm curious when you analyze the cross peak between the upper Polariton and lower Polariton, if you could see some signature of, the characteristic population transfer time from the FFCF, because it's going to transfer from a Polaritonic state to a dark mode type of state. We never did that, so that just intrigued me that this might be something interesting to look at. The other thing that we have found interesting is that the cavity can actually promote the vibrational dark mode into even hotter vibrational state. We can see it to the second excited state. So I wonder if that can have some effect onto the FFCF as well.
Yeah, sure. This sort of ladder climbing idea. I wonder how because one of the things that people know in ladder climbing is it's more efficient when the line widths and the dephasing is really narrow. And in this case, we have the 16 wave number. It's not even as broad as your acetone. Your acetone spectrum is even broader than that. But it's harder to get. We still see ladder climbing even in the normal 2D spectrum of this thing. So yes, you could imagine that you'll have some other non-equilibrium population problem that would confuse the FFCF. I mean, the other thing I should say that's funny is that we use sort of a ridiculous concentration of this stuff, right? But then when we compare it to the bare molecule, we can't do, at least not till we have our ATR setup working properly. We can't compare the same concentration of the molecule without the cavity because the absorption is so high that you can't do a normal 2D spectrum with it. So when we use the ATR trick, then of course we will be able to study the still like 100, like whatever it is, 50 millimolar or 100 millimolar concentration of this, even with the normal thing. So there could be some weird effects of the high density of the molecules. I mean, because it's not uncommon for metal carbonyls to kind of cluster up. I mean, you have the world's most nonpolar organic organometallic complex here, right? And it's in a polar solvent, so it's quite reasonable to think that they'll stick together somehow or other.
I see. Yeah, thank you.
There's a question from Xingyun Wang.
Oh, okay. I guess, right.
That's in the chat.
Yes. Jen Queen, you can ask. Yeah.
You hear me, Professor?
Yeah.
You can ask your question.
Okay, then Kevin, maybe I can read that from the chat. The question was how to control the modes in
Yes.
two-dimensional IR spectroscopy.
Yeah.
I'm not clear. I understand what you mean by how do I control the modes.
Okay.
Maybe.
Yeah. So, Professor, so I mean, my question is that so you have the curve, right? So how do you find the this mode is your experiment result? So in your 2D-IR spectroscopy. So.
Oh, are you asking about how do you get the polaritons in the spectrum?
Yes.
Okay,
yeah,
so
yeah.
the polariton, the cavity is just two mirrors that are stuck together. It looks just like a normal sample cell that you would use in a FTIR or 2D-IR experiment, except that the inner surfaces are coated to be reflective. And then you have the sample thickness is about the same as you would use in an ordinary 2D-IR experiment as well, same spacer. And you do have to have the angle set right. So this is actually super tedious because we use a pump probe geometry. If we had a collinear geometry, it'd be much easier because then you just know that whatever angle you have, you have. So the way that Rang does it is she looks at the pump transmission on the spectrometer, and she looks at the probe transmission on the spectrometer, and she has a few other tricks for making sure that the angle is just right. And we set the cavity length to be at zero tuning in that way, so that you're basically at normal, that there's a bisector, and that's the normal of the cavity. And so that you have to hit the same polariton modes, that's for sure. That's the key thing.
Yeah, thank you, Professor. Yeah.
Okay, then Thomas, you are the next.
So I just have a question. You were discussing the delocalization of the dark modes. Can you actually say something about that delocalization from the 2D spectra?
I have no idea, but so what my issue is trying to figure out how you actually get the dark mode excited when it's dark. That's the thing I don't really understand. So like I know that way, and you all have been thinking about this for a long time. Now, what we have a slightly different sort of perspective because we've been thinking about coherence transfer for a long time in 2D spectroscopy, and I can write pathways that get me those cross peaks where I have coherence transfer. And coherence transfer is a sort of a mechanism of two high frequency modes kind of being mutually coupled to something low frequency, and that allows you to break the kind of secular Redfield picture. We see that quite a bit in metal carbonyls. Could be happening here as well. And I would wonder if this coherence transfer, if one can modulate the delocalization of the dark states by, for example, changing solvent polarity, that would be a simple chemistry way of doing it, then maybe you have a way of modulating this coherence transfer mechanism, if that's what it is. It could be something totally else. I mean, he's shown, for example, you can get very long range energy transfer because if you have mutual coupling to the optical cavity with vibrations, that works quite well. So I don't really know if there's a way to test this delocalization, but I mean, so presumably it also is it's a form of exchange narrowing if you have more delocalization. So maybe that's a way that it shields it from the inhomogeneous broadening. I don't know. It's to me, this is like one of those. This is one of the areas where the chemists might have a bit more insight than the solid state physics people. But they also think about inhomogeneous broadening too.
Okay, Ricardo, you can unmute and ask your question. You are among the panelists now. Ricardo Fernandez Terran.
I think I could probably read his question. So the question is, can you
sorry,
elaborate more on the? Oh,
sorry. Can you hear me? Okay.
Yeah.
Thank you for your wonderful talk. It's mostly concerning the first part of the 2D-IR spectro-electrochemistry. This tracer normalization approach to, let's say, we are dealing with changing concentrations in a spectro-electrochemistry experiment. Maybe could you please comment a bit more about how this is done?
Yeah, sure. So we just need a way of estimating the concentrations of the different. So in an experiment, I've shown there's primarily these 3 peaks, and if we know how much those concentrations are changing, then we can scale the signals that we measure accordingly. So for example, the rephasing or non-rephasing spectra are all proportional to the number of molecules that you have. Now you need a way of figuring that out. So we measure transmission. So the way we do it is we don't get it directly from the transmission. We have to measure one spectrum of the tracer where there's no sample, then we can fit that. And then from that, we can divide that spectrum. And then that gives us, by just, freshman chemistry, Beer's law type stuff, we can get the concentration from that. And it's surprisingly functional. I mean, of course, the issue is the spectrum could wobble or whatever, but that doesn't happen so much with our optical setup, that it's actually quite fast way of estimating that. And we realized this was going to be a problem. I think Jens brought it up in his flavin mononucleotide paper too, that it's hard to get the actual dynamics because the molecule is changing all the time. So that was what we came up with it.
Okay, thank you very much.
Okay, more questions? I see none in the chat, and I see no hands risen. Okay, well, Guy, that's your last chance.
Thanks.
All right.
There's a question?
No, well, apparently not.
Okay, then let's thank both Kevin and Minjo for their nice talks. There are a few announcements before we are really finished. And one thing is that if you want to contribute, then after the vacation, there will be opportunities to speak. So if you're interested, please just submit the motivation and a title and an abstract, and then we will consider it as a talk. So we hope that we will see a lot of people that are interested in contributing. We will have another meeting on the 18th of December, same time. And we already have 2 speakers for that meeting. So Peter Ham, he's also somewhere here in the among the attendees. So he will talk about the vibrational energy transfer on surfaces, and Howie Siang-Tan will talk about correlation dynamics on molecular system with electronic spectroscopy. So I hope that we will all see you again 2 weeks from now. Maxime, you have something to add?
No, thank you very much. Then
so and maybe if there's people that want to ask further questions, you are welcome to hang around.
Yeah, you can stay longer here, no problem whatsoever. Okay, but I'm stopping the recording now.